and you had the answer key at the bottom of the page, I mean, it's out of order, and the numbers aren't going to be exactly the same, but your values should round. The answers at the bottom are generally given in scientific notation, or sorry, to the correct number of sig figs, so your answer should always round to an answer on the bottom of the page. Is there anything anyone would like me to go over from 2 and then 6 through 12? Is there anything there anybody would want me to do? Yes, Brad. Would you like, you want me to do 7? Is 7 the one you want me to do? I can do it. I can do a couple if you'd like. Okay, so is Brad the only one who wants me to do any of the homework from yesterday? All of us are good with the work. No, you were supposed to do it all. I will not do it all, but I will do a couple if you'd like. Brad, is number 7 the one you want to see?
Yeah.
Okay.
Number 10, too.
10's a gooder. Okay. 7. A motorist traveling on a straight stretch of open highway sets his cruise control at 90 kilometers per hour. So presumably that's his velocity. How far is he going to travel in 15 minutes? So the time is 15 minutes, and we want to know how far he's going to travel in that time. So this is the formula we're going to use. D equals V times T. Because if you take a look at the triangle, a handy-dandy tool to remember, I mean, you could always do the algebra, but marking your guys' test, I think we need to work on the algebra. The algebra is not overly difficult, but the triangle is useful too. D equals V times T. We just need to make sure our units are consistent first. They are not, because the velocity is in kilometers per hour and time is in minutes. So, Brad, do you want me to convert kilometers per hour or minutes or both into something useful? Yeah, so yeah, 15 minutes is 0.25 of an hour. You betcha. Yep. So then D is just going to be V times T. So that's going to be 90 times 0.25. That should be, what is that, 22 and a half? Which is, well, the answer key has 23 kilometers.
Yeah, I don't know.
As long as you got a value that rounds to one of those options down there, you're good. Okay. So if your answer is 22 and a half and they round it to 23, you're good. Kale, you wanted 10?
Yep.
Okay. Brad, if you've got another one, I'll go through it. There's a couple more people have asked if you want, and I'll look back to you after.
The last question asks for the time, but
okay.
Then the last answer asks for the...
They're not in order. The answers are not in order.
They're not?
No.
Oh.
I did say that at the beginning. The answers are there. They're not in order.
Okay.
You just need to find... And the answers for all 12 questions are there, and I only assigned 7 questions.
Okay.
So, 8 questions. So you have to, certainly do some digging. Okay, Kale wanted 10. A woman from Pasadena makes a trip to a nearby shopping mall that is located 40 kilometers from her home. On the trip to the mall, she averages 80 kilometers per hour, but she gets a speeding ticket upon her arrival. On the return trip, she averages 40 kilometers per hour. What is the average speed for the entire trip? Okay, so this is a speed question, not a velocity question. If the question had said, what was her average velocity for the entire trip, your answer without doing any work is what? If the question had asked you for her average velocity without doing, for the entire trip, without doing any work, y'all should be able to tell me the answer is? Average velocity for a round trip is always 0. Because if she starts and ends in the same spot, there is no displacement. So the question specifies speed. Now our definition for speed is this. Without the vectors, v is speed. I'll write it out here. D is distance and t is time. And if we want it for the entire trip, which we do, we need to find a total distance and a total time and then divide the two. So here's her house. She's going to a mall. Here's the mall. She goes out, she goes back. On the way there, and it's 40 kilometers from her home. So it's 40 kilometers out and it's 40 kilometers back, giving you a total distance of what? 80 kilometers. Distances always add. And so now we need to find the time. On the way there, her distance was 40. We're told on the way there, the velocity is 80 kilometers per hour. That might be useful in a second. On the way back, it says the average was 40 kilometers per hour. So there's your distance. There's your velocity. And we're asked to find the time. We need the total time. To find average speed for the entire trip, I need the time it takes to do the entire trip. So we're going to need to use the speeds and the distances for each one of these, there and back. To find the time for each, add them together, and then plug them into this. So the formula for time, if I use the triangle that I wrote down up here, I cover up time. Time is equal to d over v. So t equals d over v. If I do that for the bottom one, it's going to be 40 kilometers divided by 40 kilometers per hour. 40 kilometers divided by 40 kilometers per hour. That's going to be 1. 1 what? 40 divided by 40 is 1. What are the units on that number? I thought I heard it. Someone say it louder with more conviction. It was Ray Reed? She said? She's correct. Just be confident in your answers. You're right. Same thing with this next one. If I want to find the time there, it's going to be 40. It's always d over v. 40 kilometers divided by 80 kilometers per hour. 40 divided by 80 is? It's not 2. 80 divided by 40 is 2. 40 divided by 80 is? 1/2. Which I am going to write as a decimal 0.5. And Kai, the units on that are?
Close.
No, it's a time. Also hours. So then it took her a half an hour to get to the mall. It took her an hour to get back home. So if I want speed for the entire trip, or average speed for the entire trip, you need a total distance divided by a total time. The total distance was 80, 40 out, 40 back. The total time is going to be what? Half an hour there, an hour back is? 1.5. Add those two times together. And that's going to give you your total time. 80 kilometers divided by 1.5 hours is what? It should be 53.3. Is that what we got? Did anyone do it? 80 divided by 1.5 is 53.3 repeating, which, Brad, is the last answer listed on the thing. So that last answer is actually answer 10. Does the process make sense? So I can take seemingly simple things and make it way more interesting. Okay, are we good with 10? Okay, Brad. 9 is going to be similar. What's your question about 9? What did you do for 9? So my question for you then would be, how does an echo work? Sound goes out and has to come back. So what should the distance be? No, displacement would be 0. Distance is going to be what? 280.5 times 2. And then that's the distance that you're going to divide by 340 to give you the time in seconds. Question number 9, an echo goes there and back. Good question. Anybody else will have anything they'd like me to do? Either you're all very good or we did not do our work. Yes, Alana. I can do 12. Dwayne, what did you want me to do? Also 12. Love it. Okay, 12 is a good question. A supersonic jet travels once around the Earth at an average speed of 1.6 times 10 to the 3 kilometers per hour. So we're given a speed of 1.6 times 10 to the 3 kilometers per hour. For those of you who don't like scientific notation, that's 1,600 kilometers per hour. Let's move the decimal space 1, 2, 3 back. Its orbital radius. Good question. So here's the Earth. Plane's going around the Earth. Here's my plane. Plane follows a path around the Earth. And we're told that the orbital radius, so the radius of that circle is 6.5 times 10 to the 3, or 6,500 kilometers, or just kilometers. Just kilometers, yeah. It's a distance. And we want to know how many hours it takes. So if they give you the radius is just from the center of the circle to the outside of the circle. That's not actually the length of the path. What is it called to find the length of the path around a circle? It has a name. Sorry, louder. I think I heard it. Say it louder, whoever just said that. You were right, if it ever helps. I want everyone to hear it. Yeah, we need the circumference of that circle. So the path that the plane flies is the circumference of the circle, and the circle has this radius, 6,500. So this is going to be, we want to define the circumference. I don't necessarily expect you to remember, but you could ask or you could Google it. Circumference is 2 pi r. So to find the circumference, it's going to be 6,500 times 2 pi, because they give you r, the radius. So your circumference, or the length of the path around the circle, times 2 times pi, is 40,840.7045. I'm not going to round till the end. So then this becomes our distance in kilometers that the plane actually flew. So then to find the time is distance traveled divided by speed at which you traveled. So then this is going to be that 40,840.7045 divided by 1,600. And unless I screwed this up, it should be 25.5, which I would round to 26. Which your answer key rounds to 26 as well. Is it on the screen there? It is on the screen there. And that's that value right there. That is how you would do that question. Conceptually, simple, like the physics it's one formula. It's a combination of d equals vt, v equals d over t, or t equals d over v. But you can tweak some of the details and make it way more interesting. Alana, does that make sense? Dwayne, it makes sense? Okay. For those of you, if you didn't do 12, I would put a little star next to a question like 12. Might be useful to know how to do a question like 12 in a couple weeks. Hint, hint. Tossing that out there for you to do whatever you want with that information. No meaningful. Okay. We understand what I'm saying, right? Do I have to be really clear with what I'm inferring? Like, there's not a lot of reactions on some people's faces. Do I need to explain what I'm inferring, or do we all follow? Chapter's going to be over in a couple weeks. In physics, we often have tests at the end of our units. Nothing? No? Okay, cool. Okay. Ooh. Yes. I need to find my other booklet for this. I was last week. Okay. Let's look at some more graphing today, shall we? Here we go. There's an extra page in there that I left for you to do some of this work on. So flip ahead, find me this guy. Nope, yep, that guy. Here we go. Okay, so there's no title on this, but there definitely should be. What we're going to look at now is a particular kind of graph. You kind of already looked at these already, but we're going to look at them in more detail. We're going to look at, they're called a few different things. It really depends on what's on this axis here. Sometimes these are called position. Sometimes they reference distances. Sometimes they represent displacement. All these, the titles are not interchangeable. It's whatever's labeled here on the side. But we treat them all the same way, and they have very similar properties. What we're going to look at now is position, distance, or displacement versus time graphs. A rather useful tool. There we go. Over. Love it. So this particular graph is it's demonstrating something you've seen before. It's similar to the swimmer one that I gave you a couple days ago. We've got a position in meters north. So that's what the positive values are all meters north. Negative ones would then be the opposite of north, which is south. And when you're measuring, if you're looking at or plotting positions, and then moving between them, yes, it says position there, but really what we're looking at here is a displacement graph. Displacement versus time. Because what's happening, we're labeling positions and then we're moving back and forth between them. So a change in a position is a displacement. This is a displacement versus time graph. So given a graph like this, a displacement time graph, we can find a bunch of stuff. We can find positions at particular times. Relatively easy to do. I say, where is, I don't know what the graph is. Let's say it's a bug. Where's the bug at 5 seconds? 30 what? 30 meters north. You bet. You went to 5, you went up. Relatively easy. We can find distances covered. We can compare different positions. We could add the travels up. We could look at displacements. Displacements are just changes in position. The bug was here, now the bug is there. What is the displacement given a particular length of time or time frame? When we combine looking at displacements and distances with the fact that we have a timeline on the bottom here, what else can we find on a graph like this? If I start combining distances with times, what am I looking for? Kale, do you have any thoughts about the bug? If I combine some of these concepts, if I look at if I say as I find the distance traveled or displacement between two times, and I use the time scale, what concept can we find? What have we been doing? Yeah, Yuli. Yeah, we can find speed or velocity. Because finding a speed or a velocity is just looking at how a distance has changed divided by the time it took to make the change. That was the whole point of yesterday's lesson. So a graph like this, just seemingly lines on grids, can give us a whole ton of information for whatever it is we're looking at conceptually. So let's take a look at these things. Given a displacement, the displacement at a given time can be found by, scribble this up. We are not reading the displacement because this is it's not measuring displacement on the side, it's measuring position. So if I wanted to find displacement at a given time, what are we actually going to do? Well, we're going to read positions at whatever time we're looking for, at a time or at times. And then to find a displacement, if you recall from our second day on this unit, displacement is a change in position. So it's your final position minus your initial position. And if we're going to be really clear about what it means for there to be a final position and an initial position, your final position is I'm not trying to divide this by anything, but a final position is just the later time, because time only goes one way, and this guy is your earlier time, which does go without saying, but then I don't say it, and then people go without. So for each one of these, let's assume that initial, if I spelled initial properly, that would be useful, IAL. Let's assume initial time equals 0 for each one of these. So compared to the beginning, what's the displacement of our bug after 3 seconds? At 0, our bug was here at 0. So with initial time being 0, initial position also equals 0. Our bug started at the origin. So what's the displacement of our bug after 3 seconds? Take a look at the graph. 30 what? Meters north. After 5 seconds, what was the displacement? Sorry? We go to 5 seconds, we go up to the line. It's still at 30 meters. So what happened between 3 seconds and 5 seconds? If the displacement hasn't changed, what must be true for our bug for this window of time here? Didn't move. Interesting result. At 8 seconds, where's the bug? Back at its initial, so what's the displacement? 0. And then at 9 seconds, where's the bug? -20 meters south, or, and Kale, you just said -20 meters. Yeah, you bet. So those are displacements. Let's just for fun go and talk about distances. Those are displacements. What about distances? Just to review. What's distance traveled after 30 seconds? $30 meters. Notice how Ray Reet did not give a direction and I didn't correct her. Distance is a scalar, not a vector. We don't care about direction. After 5 seconds, what's the distance traveled? It still has only covered 30 meters. After 8 seconds, what's the distance traveled? 60. Remember, distances only add. So if after 8 seconds our bug has gone out 30 and then come back 30, 30 plus 30 is going to be 60 meters, because again, distances only add. What's the distance traveled after 9 seconds? It's going to be 80 meters. Oh, sorry, I'm not even on the screen. Nobody said anything. So depending on what you're being asked for, you got to think about it a couple different ways. When you're ready, flip the page. Yuli said it already. We can find speeds and velocities too if we want. Speeds and velocities are just connected to distances and displacements on our position time graph or our displacement time graph. I want you to flip to this page. I'm going to flip back to the picture here. If I take a look at what we've got here and I say, okay, well, I want to go ahead and I want to find the speed traveled for a particular length of time, I want you to be on this page. I'm going to be on this page for a second. Take a look at the graph of what we've got here. Yesterday, we talked about how a velocity is a displacement divided by a time. So if I want to look at that for this one, what is our velocity for 0 to 3, that first 3-second window? Well, what's the displacement for that first 3 seconds of time for our bug? Someone just say it again. Displacement over 3 seconds is 30 meters north. You betcha. But if you look at it, that's just, we just went up here from our x-axis or our time axis up to the value. And displacement is, velocity is displacement divided by time. Well, the length of time is just going to be 3 seconds. So if velocity is displacement divided by time, and this is our displacement and that is our time, what are we actually finding here? Think back to Math 10. On a graph, when you took a vertical distance on a graph and divided it by a horizontal distance, what concept were you finding? Slope. So on a position time graph or a displacement time graph, average velocity can be found by calculating the slope of a line segment. And if you recall from Math 10 slope is equal to a rise over a run, but on a graph like this, the rise is just your displacement, the run is just your time. And so now instead of just calculating random slopes for pointless lines in Math 10, we're giving it meaning. So if we want to find the average velocity from 0 seconds to 3 seconds, we just go ahead and find some slopes. From 0, I'm going to flip back and forth. You don't have to. From 0 seconds to 3 seconds, our slope is a rise over a run, so it's going to be 30 over 3. So if I flip back here and take a look. The velocity is equal to the slope, which is just the rise divided by the run for a particular segment. The first segment rises, and we want to use the values on the side, the scale for the graph. The rise was 30 meters north. The run was the length of time, so 3 seconds. So average velocity is what? 10 meters per second, and it's velocity, so you need north. Found the slope of a line segment. Cool. From 3 seconds to 6 seconds, I'll flip back so you don't have to. From 3 seconds to 6 seconds, it's this flat line right here. You guys would have learned last year that when you were just talking about generic slopes, the slope of a flat line is 0 because there's no rise. I think it was Ray Reet a second ago who said that the bug from 3 seconds to 6 seconds wasn't moving. Was that you, Ray Reet? So if something is not moving, it has a, wow, sorry to be boring you, Kai. If something is not moving from 3 seconds to 6 seconds, its velocity then is going to be, I know it's the end of the day. It's the last block on a Tuesday. Put it all together, guys. From 3 seconds to 6 seconds, it's got a flat line. Slope equals rise over run. Conceptually, Ray Reet was right to say this guy in here is not moving. But what does it mean to be not moving? Well, let's do the slope calculation. There is no rise from 3 seconds to 6 seconds. And 3 seconds to 6 seconds just so happens to be 3 second interval. So if the slope is 0, the units on that are going to be meters per second. Things not moving. From 6 seconds to 9 seconds, let's take a look over here. I'll flip back so you don't have to. 6 seconds to 9 seconds is this segment of time right here. From here all the way down to here. Now if you look, you'll see that this line is straight the whole way through. And to find the velocity of our bug over this 3 second window, the 6 second to 9 seconds, we just find the slope of this whole segment. What is the slope of that segment? Well, there's the rise. There's the run. What's the rise on this graph? Sorry, Kale? Almost. It's a rise that goes down. Negative 50. And the run is 3 seconds. So we can go ahead and we can do that. If we want the velocity, velocity is equal to the slope on a displacement time graph. Slope is equal to the rise over the run. Kale said the rise was negative 50 because it goes down. Divided by the 3 seconds it took to go down. Negative 50 divided by 3, I'll do that for you, is going to be negative 16.6 repeating. And now we have to give that to units, and because it's velocity, we have to give it a direction. If the displacement, remember the rise represents displacement, if the displacement is negative, what's that direction? It's going to be south. The units were meters, so we're going, or meters per second rather. So our bug is moving 16.6 meters per second south. For the last one, from 0 seconds to 6 seconds, I'm going to flip back so you don't have to. There is no line segment on this graph from 0 seconds to 6 seconds. The segments go from 0 to 3, and then 3 to 6, and then 6 to 9. So this is where it starts to get, you have to be able to go back and forth in your brain relatively easily. What are the equivalent ways to think about velocity. If I want to think about velocity, I've been doing it one way this whole time, but there's two ways to look at it. Velocity is always a displacement divided by time. So if I want to do that now for the 0 second to 6 second mark, I can go back and I can take a look. What is the displacement from 0 seconds to 6 seconds? Almost.
30 meters north.
There you go, 30 meters north. That happened in the first 3 seconds, and then it stayed there for the next 3 seconds. So our displacement was 30 meters north. 0 seconds to 6 seconds is a 6 second time interval. (30 divided by 6 is 5. That should be seconds. So meters per second north. So practically speaking, if this is what we've calculated, what have we actually done here? What we've done here is we've actually found the slope of the line that connects these 2 points on the graph. So this line, oh, almost that line. That line right there is effectively what we've done. We took our starting point, we took our ending point, and we found the slope of that line. And being able to read and pull information off a graph like this is an important skill to have. Questions, comments, concerns about what we've just done here? Slopes are something you guys should have spent way too much time calculating last year. And now all I'm trying to do is give it some meaning. Comments, questions, concerns? Cool, then flip the page. There is another concept that we can look at here. Here we go. So, there's a concept here called instantaneous velocity, and above here I want to make a couple notes before we actually go ahead and find that. Average velocity. We've calculated it already. We referenced it a little bit. Average velocity, we said, was... I'm going to be overt here about what I write. V, and then this is AVG. So average velocity, we said, was found by calculating your displacement, or your change in position, over how long it took you to make that change. But sometimes the time frames for this are a little bit weird. And the example that I like to use for this is we're looking at like some of these old school GPSs. Now, because you all have smartphones, you may not have had an opportunity to use an old school GPS. Hands up if you've used an old school GPS, not one tied to your smartphone. Henry, you have. Okay, one of you. I've never seen this on Google Maps, but what the old school GPSs used to do is they used to give you statistics for your trip. So a buddy of mine and I, when I was in university, we decided we wanted to go for lunch in Kamloops. He had just gotten a brand new car. His brand new car was a speedy little thing. And so we decided we are going to go for lunch in Kamloops because we can. It was a fall morning. The Coquihalla was basically empty. And I set my land speed record that day. And we looked at the thing, and it told us that for our trip, the whole trip, our average velocity was 110 kilometers per hour. But if you think about what average velocity talks about, what does average velocity take into account? It takes into account your change in position. So my front door, where he picked me up, and we turned on the GPS, to Boston Pizza in Kamloops, whatever that displacement is, divided by how long it took us to do that. And that was the calculation the GPS did. It said our average speed was average velocity was 110 kilometers per hour. What does that take into account? I don't live on the freeway. So that average velocity takes into account all of the regular city streets that we drove, any school zone that we went through, any time that we spent sitting at stoplights, and then we got onto the highway. So it took into account a whole bunch of time spent at well below 60 or 70 kilometers per hour, and then enough time above that it averaged it out to be 110 or so kilometers per hour. I'm a little bit ashamed of my record. 198. No, I'm only ashamed because I was so close to breaking 200.
Oh, yeah.
That's why I'm ashamed.
Yeah.
I shifted too early into 6th, and it lugged a little bit, and the corner was coming, so I had to ease off. I almost broke 200. He hit 220 on the way back. But that was down the hill through the snow shed. We were flying in his little Honda Civic. It was awesome. But I digress. So average velocity, it's important to recognize, takes into account things like all the time you spent displacing yourself between two spots. What we're going to look at right here is called instantaneous velocity. And instantaneous velocity is actually the one that you're probably most familiar with. When you're driving your car and you're looking at your speedometer is telling you how fast you're going now, which actually doesn't necessarily make a lot of sense, because if you freeze time right now, you are at a point. So how does it know? Like right now, I haven't moved. It's an infinitesimally small length of time. So how could my speedometer possibly be telling me how fast I'm going in an instant? Because the only way to determine how fast you're going is by comparing how far something's moved over a particular length of time. I don't know if I'm making sense. If you're seeing the issue here. So calculating instantaneous velocity is a bit of a beast, because an instantaneous velocity means you're taking velocity at an instant, and it doesn't make sense for there to be any time traveled over in an instant. So that's this concept here. Instantaneous velocity is the velocity, or your velocity, at a moment in time. And as far as the physics goes, you have no way of calculating that. There is no way at this stage with your guys' mathematical skill set to say, I'm just going to make this time, remember this is a time interval, I'm just going to make that 0 seconds because I want to know how fast I'm going right now. As soon as you try to divide by 0, your calculator is going to give you an error because you cannot divide by 0. So how do we actually go ahead and find out how fast you're going right now? To do that, at this stage, we graph. And you've seen these things already. If I give you a curved graph, this is going to be position. Position. And if your position is changing and that position is curved, the line here is getting steeper. If a curved line is getting steeper, that means that as time is progressing, the slope is getting steeper, and if slope is velocity, what's happening to our object in this graph? It's accelerating. So this is our introduction to the idea that speeds can actually change, which you're familiar with already, but the math is kind of interesting. So on a curved line like this, the line is getting steeper. So the object must be moving faster. If an object is moving faster, as Yulia said, it's got to be accelerating. And if the slope, or if the line rather, is constantly curved, that means the acceleration here is going to be constant. And if you're constantly accelerating, how do we figure out how fast you're going? To do that, we draw what's called a tangent line. So I'll show you what that looks like. And you're going to practice this for me here a little bit. You are, if we look at this thing right here, let's say I want to figure out how fast I'm going at this time. I don't know what this time is. Let's say it's 5 seconds. And this whole line is curved. Because the whole line is curved, the velocity isn't constant, the thing is accelerating, but I want to figure out how fast I'm going at a moment in time. What we want to do is we take a ruler, and this is going to take some practice. We're going to spend a lab practicing this. We're going to figure out how we can best approximate that curved line by drawing a straight line that just touches the curved line at a single point. We draw this guy here. This line has a name. It's called a tangent line. Now, I don't think circle geometry is taught anymore in grade 10. It used to be. A tangent is a line that touches a curved line at one point. It doesn't cut through the graph anywhere. It just touches at one point. Touches just at one point. And it's for reasons like this that I've been telling you guys that when you do graphs, I want you to use as much of the graph as possible. Because to find a velocity at a particular point, we need to draw a line that approximates the curve at a particular point, but that line's going to go on forever in either direction. And now to figure out how fast we're going there, we just have to figure out what this whole slope is. So then the velocity at that moment, that instantaneous velocity, is going to be equal to the slope. So instantaneous v is going to equal the slope of the line that touches at one point. For those of you, I'm going to put a little note down here. For those of you who see yourself going on and taking a calculus course, I want you as best as you can to remember what I've said here, and then in a year or two, when you've taken a calculus course, I want you to think back to this and be like, there is a connection between what I'm learning here and what Dawidoff tried to show me in Physics 11. There are mathematical tools that will do this for you in very powerful, very easy ways. You don't have them yet, so we have to put rulers on paper. But there are really, really awesome techniques for this. So we're going to practice this in a lab that we're going to do, but not yet. So that is how you find instantaneous velocity. We will revisit this. Okay, so I'm going to give you a couple examples of some displacement time or position time graphs. Here is one. For this object, if displacement isn't changing, what can you tell me about the velocity for this object? Velocity is 0. Displacement doesn't change. Cool. How about that guy? What can you tell me about the velocity for a graph that looks like this? Yeah, Kai.
It looks like 1/1.
I mean, we don't know what the scales are necessarily. You're suggesting, if the scales are even, Kai, you're giving it a value. You're suggesting it's 1/1. Okay, that's more detail than I'm going to ask you to assume. What can you tell me about, don't give me a value for it, but what can you tell me about the slope of this line? Yeah, Yuli. The slope doesn't change, and so the velocity is constant. You betcha. Whatever that value is, the velocity is constant because the slope isn't changing. There's something else that you can tell me here. When you guys were looking at slopes back in Math 10, a line that moves up to the right has what kind of slope? Sorry? Positive. So in this case, the velocity is both constant and it's positive. And so what that tells us is that whatever our object is moving in a positive direction, whatever you've defined it to be, constantly. Cool. How about this guy? This is the curved one we just looked at. It's curved and getting steeper. So velocity is doing what? You're going to see in a couple days how that is an insufficient answer. You're right, Kale. This object is accelerating. How is it accelerating? When you say accelerating, what do you mean, Kale? Getting faster, okay? So if you're getting faster, velocity is increasing. The reason I'm being picky here with the language, Kale, is because in a couple days you're going to learn that we use accelerating to mean velocity is changing. The word accelerating does not differentiate between speeding up and slowing down. You guys are familiar with accelerating meaning to be going faster. I'm going to change the definition of that word for you in a couple days. Accelerating means slowing down or speeding up. And we're going to add that positive or negative to it. So velocity here is increasing, and it's positive because it's above that axis. Let's draw in 3 more here down on these empty axes down here. We're going to look at this guy, and this guy. Let's go to the middle one first. The middle one's the easiest. What does this mean? On a displacement time graph, what does a velocity, a line that looks like this, mean? It's similar to the one that's above it. What can you tell me about that slope? Maybe I should have used a ruler. What can you tell me about that slope? It's negative. The line is moving down to the right. So that's a negative slope. What else can you tell me about the slope? Is the slope changing? No, Caitlin, it's not. You are right. So that is a constant slope, which means that is this graph, or this kind of line on a position time graph, means the velocity is constant and it's negative. A negative velocity just means that you're traveling in a negative direction. So we have an object that's moving back. So these guys here, that guy, these positives and negatives here are just directions of travel. Okay, what's happening here? What do you mean it's decreasing?
Negatively accelerating.
Okay, so Kai, you're suggesting it's negative. Why do you say it's accelerating? What about the graph says that to you? You're right. That helps you. Why are you using those words to describe that line?
Over time, it's going slower, more quickly.
You were so close, and then you lost it there at the end. Is it going slower? If I take a look at the line that we've got here at the beginning, if I'm going to take my ruler and I'm going to put it up against that graph, that ruler is flat, yeah?
Yeah.
So if the ruler is flat, what's the velocity at the beginning? Constant with 0. A flat line on a displacement time graph means the thing's not moving. As time increases, what's happening to my ruler? As I roll it along the line, it's getting more steep. So if a line on a position time graph is getting steeper, what's the velocity doing? Kale. The line is getting steeper. If the line goes from 0 to steeper, the slope is increasing negatively. The thing's getting steeper. So what does that mean then for this object? It means it's not slowing down. It means it's actually speeding up backwards. Because the slope is getting steeper, means velocity is increasing, and the direction that it's increasing, and you guys said it was, Kai, you said it was negative. This, again, just the direction of travel. Speeding up, heading backwards. So then this one, this last guy here, starts with a steep line and drops down to 0. So what's that graph, or what does this kind of curve on a position time graph mean? Sorry? It's decreasing. So if your velocity is decreasing, commonly we would say that the object is doing what? Slowing down, yeah. This is what decreasing velocity looks like, and this thing just so happens to be decreasing negatively because it's dropping. Okay. This is new. Here's what I'd like you to do. On the next page is blank. Here is what I would like you to draw. You do not need a ruler. You can freehand this thing. I'm not going to ask you for specific values for anything. I don't have scales on here. I just want you to draw me that thing. There are J points, so 10. J is 10. There are 10 points on here. There's a flat line, then it curves up, then it goes straight, then it curves down, then it's flat, and it's a diagonal line that does not curve, then it's flat, then it's curved, then it curves the other way, then it's flat again. I want you to draw me that. As best you can. I'll print this off. I'll print it so you don't have to worry. Unless you want to, I'll print it off. Okay, give it a shot. Draw me that. And put in the marks that I've got in here for you. Toss those in there. I've defined a couple things for wait. Okay, then I'll see you later. I've defined a couple things here for you. I give you a title. This is a position versus time for a person on the 3rd floor. The starting point here is the superlab. This is position in meters west. So if that way is north, then west is that way into the board. So the 3rd floor hallway actually runs east-west. We are at the west end of the hallway. We'll call that the end of the hallway. And we'll call 0 the rotunda.
That's yellow.
Yep. I would like you, for the time that remains, with the people around you, to discuss and create for me a description of what could be happening in this graph. We did a stupid simple one to start. I had 3 lines, the bug was at 0, the bug walked out, the bug stayed there, and then the bug went back the other way. Let's give you a ridiculous one. What's happening, based on the individual pieces that we've drawn here, what's happening on a graph that looks as ridiculous as this? That is your task for the remainder of the block. With this graph, paint me a picture, tell me a story, what's going on for this person on the 3rd floor. Discuss. Go. Be as deliberate as you can. Talk about speeding up and slowing down. Give me a description. And then one of you, once you've decided on something, I want one of you to record what you've decided on. What's the description of the person doing this motion? I want you to flip the page and look at questions 1 and 2. That's going to be for homework as well. Tomorrow we'll continue our discussion on these graphs. And if we've got time, move on to acceleration. I'd ask that you work. Don't pack up, Riri. You have time. You could probably get these 2 questions done in the time that you have. You have 5 minutes. And we, really didn't use the discussion time I wanted you to use. You guys were all sitting there quietly. I looked. Get these done. When the bell goes, you can go.
Just run for the washroom super fast.
Yeah, you got to graph it though.
A graph?
No, go. You can go. Go to the washroom. If your table did not discuss, then that picture is your homework. If you need me to flip back, take a picture of it. I want a description of this motion. And I want the top 2 questions done. When the bell goes, you may also go. Have a good day.